Okay, Bismillah ar-Rahman ar-Rahim. So I'm restarting the recording again. So today is February 22nd, 2021. And today we'll cover the topic of joint probability distributions. Of course, today we'll have quiz 3 within the class. Next Wednesday, we'll do a review for the midterm, at least part of the lecture. So let's start today's lecture. It's very common that we will not be studying a single random variable at once. Usually random experiments encounter more than one random variable in the same time. So, and it's very often that we want to study their joint behavior and to check how do they affect each other, are they related, are they independent, and so on. And there are many examples that can describe this. Like in almost all health studies, we see many variables that interact with each other, like the height, the weight, the age, the cholesterol measures, and so on. So all of these are different random variables that interact with each other. Also in product manufacturing, usually like in side dimensions and length dimension. They usually interact with each other. So we want to study the joint behavior to start with of two random variables. Say x and y, and we want to characterize their joint behavior, their interaction. So, for example, let's do a quick example. Assume that we did a study about the relation between signal strength on your mobile phone and the number of times you need to repeat the name of the city you are asking about with an agent on the phone. So the scenario is you are calling a travel agent or the airport or any agent that you need to spell a city name to that agent, and then we want to study the relation between the strength of the mobile signal and how many times you need to repeat the name of the city you are asking about to the travel agent. So you will call the number and then you will tell the agent that I want a ticket to London, and then he if you have a weak signal, he will ask you, can you repeat that? Then you say London. Can you repeat that? London, and so on. So, and we did some kind of statistics, and we found out that this can be described by like X is number of bars on your signal. So it can be 1 bar, 2 bar, or 3 bar. Y here, y is number of times you repeat city name. And then this can be 4, 3, 2, 1. And then we found out that the probabilities are given by 0.15, 0.1, 0.05, 0.02, 0.1, 0.05, 0.2, 0.25, 0.02, 0.03, 0.02, 0.01. As you can see, let's look at this table. If 3 means strong signal, so if you have strong signal, the highest probability that you will need to repeat the city name only once. If you have a weak signal, it's high probability that you will need to repeat the city name 4 times, and so on. So each entry in this table, each entry in the table reflects the joint probability of X and Y. So for example, let's say if we say this 0.1, so it's the probability that X equals 2 and in the same time Y equals 3 is 0.1. 0.1, which is 10% of the time, you will have 2 bars on your mobile phone, and when you call the agent, you will need to repeat the city name 3 times for the agent to understand what you mean. And the way we characterize joint probability distributions, we characterize joint distributions using joint probability mass function, which is, we write it as fxy of x and y, or simply f of x and y. And the way we define it is, it's the probability that x equals small value of x and y equals small value of y. Of course, f of x and y is a probability. So for discrete time, it's a probability. So we can say that we start with discrete joint distribution. F of x and y is a probability, which means that f of x and y is greater than or equal to 0. It should be positive. Also, summation, we used to sum over x. Now, if we sum over x and y, we should get 1. So let's check this example, if this is a valid f of x and y. If we sum all the probabilities in the table, they should add to 1. So 0.25, 0.45, 0.5, 0.55, 0.65, 0.75, 0.8, 0.95, 1. So yes, this is a valid probability distribution because they are all greater than or equal to 0, and the summation is 1. So we can ask, continuing with the example, we can ask, what is probability that you need to repeat the city name 3 times, which means the probability that y equals 3. Probability of y equals 3 is simply, it consists of 3 scenarios. Probability of y equals 3 when we have 1 bar, or we have 2 bars, or we have 3 bars. So if I am interested in probability of y equals 3, I have to add. So probability of y equals 3 is the probability that y equals 3 when x equals 1, plus probability of y equals 3 when x equals 2, plus probability of y equals 3 when x equals 3, which means that I have to sum the 3 probability 0.02, 0.1, 0.05, 0.02 plus 0.1 plus 0.05, which is 0.17. Similarly, we can ask, what is the probability that you have poor signal, which means 1 bar on your phone. So 1 bar on your phone, it means that, let's use this, 1 bar on your phone, it means that you have to add 4 probabilities. This is 1 bar when y is 1, and y is 2, and y is 3, and y is 4. So simply, probability of x equals 1, probability of x equals 1 is probability of x equals 1 and y equals 1 plus probability of x equals 1, y equals 2, plus probability of x equals 1, y equals 3, plus probability of x equals 1 and y equals 4. And then we need to sum all of those probability, 0.15, 0.02, 0.15 plus 0.02 plus 0.02 plus 0.01, which is 0.2. Also, you can ask any question. What is the probability that x is less than or equal to 2 and y is less than or equal to 1? X is less than or equal to 2. Let's see. Let's use a dark green. X is less than or equal to 2. So 2 or 1. So this is for x. And then at the same time, y is less than or equal to 1. And y is less than or equal to 1, which is this. So basically, we are talking about only those 2 probabilities, which is 0.01 plus 0.02, which is 0.05. 0.03. Okay, and so on. You can define any range or any probability that we are interested in. طيب. For continuous random variables, we also have the joint BDF. Instead of mass function, we have the joint BDF, and we'll use the same f of x and y. And here again, f of x and y is not defined as in discrete, meaning that it's not probability that x equals x and y equals y. Rather, we say that probability of x and y are in a certain region R is the double integration over that region of the joint BDF x and y. We'll not talk much about the continuous joint probability distribution. Will focus more on the discrete, but it's the same analogy. If you have there double summation, here you have double integration. Also, know that if we double integrate from minus infinity to infinity, f of x and y dx dy, it should give us 1. So here now what we have so we have a curve that's three-dimensional curve, and what we are saying is that the volume under the curve in 2 dimensions equals to 1. So in the continuous random variables, we'll have 2-dimensional curve that has a volume of 1 underneath, and it's always positive. So we should have written this, that f of x and y is greater than or equal to 0. We can have a quick example in the continuous. Given f of x and y equals cxy, where x between 0 and 3 and y between 0 and 3. Find c to make this a valid f of x and y. Want to find c that makes this a valid f of x and y. So we said the volume under the curve should be 1. So how do we calculate the volume? We calculate the volume using double integration. So integration from 0 to 3, from 0 to 3, cxy dx dy. This should be 1. So c is a constant. You can take it outside. Integration from 0 to 3, from 0 to 3, xy dx dy. So first you integrate with respect to x. When you integrate with respect to x, y is a constant, so x squared over 2y from 0 to 3 dy, which is integration from 0 to 3, 9 over 2 minus 0 y dy, and we have c, of course, outside. So we take also 9 over 2c outside, and then we are left with just y dy, and then this is again 9 over 2c, y squared over 2 from 0 to 3, which is c times 9 over 2 times also again 9 over 2, and this should be 1, which means that c should be 4 over 81 to make the volume 1 and f of x and y to be valid. As I mentioned, we will not focus much on the continuous case. It is the same. In continuous case, we'll have two-dimensional curve. In discrete case, we'll have two-dimensional table. So I will not have only x and f of x. We will have two variables in a table, x and y, and then we will describe their joint probability. Okay. طيب. Moving on, we'll define what we call marginal probability distribution. Which is basically given, if I give you f of x and y, how can we find f of x and f of I alone? And in this case, we'll call those the marginal distribution. If that f of x and y is the joint, those will be called, in this case, marginal distributions. And again, this is very common. If you have an experiment that has many random variables interacting with each other, then you might be interested in extracting one of the random variables to study its behavior individually. You want to study the weight individually. You want to study the length of the product individually, aside from all other random variables. So we'll talk now how to calculate the joint probability distribution, the marginal probability distribution from the joint probability distribution. And in very simple case, or in a very simple equation, as we'll see in the discrete case, what we will be doing, basically, we will be one second, sorry. I missed one thing that. Okay, don't worry about it. So, for the going back to our example, to the above example, we had, if you recall, we had x, here we had y, and then x was 1, 2, 3, and y was 1, 2, 3, 4. And I think I have the numbers somewhere. Let me write the numbers again. Okay, so let me write the numbers again. 0.15, 0.02, 0.02, 0.01, and 0.1, 0.1, 0.03, 0.02, and 0.05, 0.05, 0.2, and 0.25. Again, if you want to check whether this is a valid distribution, you have to add all probabilities in the table, and they should add to 1. So now assume that we are interested in f of y. We want f of y only. To find f of y means that, so to find f of y, that y can be 1, 2, 3, or 4. So you should give me y, f of y. You should give me y for 1, 2, 3, 4. And what's f of y? And in the case of discrete random variables, we know that f of y is simply probability that y equals y. So if I give you the joint distribution of x and y and ask about the marginal distribution of y only, what you need to do is to find the value of f of y for 1, you just sum across all possible x's for that 1. So if you sum all of those, so 1.15 plus 0.1, 0.25 plus 0.05, this will give you 0.3. Sum over x. For the 2, you sum again, and you will get 0.02 plus 0.1, 0.12, 0.1. And for the 3, 0.02 plus 0.03, 0.05 plus 0.2, 0.25. And for 4, 0.25 plus 0.03, 0.28. So this is my f of y alone, 0.17, 0.25, 0.28. And you can always check that this should be also a valid probability distribution. So if you sum all of those, they should add to 1. How about f of x? X has 3 values, 1, 2, and 3. So you should give us x, f of x, 1, 2, 3. And what's the value of f of x? Again, f of x is simply probability that x equals small x. So again, in very similar manner, if you want x, you sum across all values of y. For 2, you sum here like this. For 3, you sum. So if you, for 1, it's 0.15 plus 0.02 plus 0.02 plus 0.01. So this is 0.2. And here 0.2 plus 0.25. And then 0.25 plus 0.2, 0.45, 0.5, 0.55. So 0.2, 0.25, 0.55. So what does this tell you? It tells you that 55% of the time you have a good signal. You have a signal with 3 bars, while 25% of the time you have only 2 bars, and 20% of the times you have 1 bar on your mobile phone. So to find the marginal distribution, we sum. If we want y, we sum over x. And if we want x, we sum over y. This is what we basically did here. If I want x, I sum over y. If I want y, I sum over x. So this is the way to find the marginal distribution in the discrete domain. Right. How about if we want to find, let's do another example. Let's do a quick example. Or in here, without, let's follow up in this example. If I ask you, find mu x, what's the mean of x? Very simply, mean of x is expected value of x is just 1 times 0.2 plus 2 times 0.25 plus 3 times 0.55, which is 0.2 plus 0.5 plus 1.65, which is 2.15, 2.35. So this is the mean of x. So on average, you will have 2.3 bars on your mobile phone. Again, we mentioned before that the value of the mean should not necessarily be part of your range. The mean is just indicates the center of gravity for the values, the possible values of your experiment scaled by their own probabilities. And of course, you can calculate the variance, you can calculate the mean of y, you can calculate the variance of y, and so on and so forth. I will not talk about marginal distribution for the continuous domain because as I said, we will focus in the joint distribution on the discrete. So let's stick with the discrete and let's move on to talk about conditional probability distribution. Conditional probability distribution, we talked about conditional probability in the past. Recall that. We talked before that probability of B given A is just probability of the intersection divided by the probability of the event that happened already. So now we can rewrite this in terms of joint and marginal distributions. Simply as f of y given x of y, because x already happened, this will be just the joint of x and y over the marginal of x. So just rewriting the conditional probabilities in terms of the joint and the marginal. طيب, let's see how can we apply this. So if I tell you, for continuing with the same example, what I can ask you, given that you looked at your phone and you know that the phone has 1 bar, which means you know that x equals 1. what is the probability that y will be 4? Which means, what's the probability that you will need to repeat the city name 4 times if you know already that you have only 1 bar on your phone? If you go back to your table, as you can see here, we are focusing now about x equals 1, and we want to check the probability that you will need to repeat. Oh, sorry, and it seems that that's why I was wondering. These are inverted. It should be 1, 2, 3, 4. Because if you have, I hope maybe if I'm not streaming this, one of you could have picked this up. If the signal is weak, you should have higher probability for this event, which is you have to repeat the city name 4 times. It should be more probable than repeating it 1 time. So for me not to confuse you, let me do another example. So we don't want to continue with the same example because it will not make sense now. Okay, let's do another example. That's fine. Example. Given the following distribution, x, y, f of x and y. So x can be 1, y is 1, and this have 1/4 when x is 1.5, and y2 is 1/8, 1.5 and 3, 1/4, 2.5, 4, 1/4, finally 3, 5, 1/8. So this is the joint distribution. In this case, you can probably, if you want to plot it, we can plot it. This is x, this is y, and x 1, 2, 3, 4. 1, 2, 3, 4, 5, and x can be 1, 2, 3. So x 1 and 1, we have 1/4. When x is 1.5 and y is 2, we have 1/8. Also, when x 1.5 and y 3, it's 1/4. When x 2.5 and y 4 is 1/4. And when x 3 and y 5, we have 1/8. So this is the joint distribution. So now what I'm asking, I can ask question, find f of y given x equals 2.5. We know that x is already 2.5. What's the chances that what's the distribution of y? So f of y, given that x equals 2.5, equals what? Equals f of y and x equals 2.5 over f of x equals 2.5. So y and x equals 2.5. How many options do we have? When x, talking about here, right? So f of y, and what's the joint of, do we have any other possible values of y? It's only one value when x equals 2.5. So this is, the joint is just 1 over 4. Once f of x equals 2.4, 2.5, find the integral of x, we have to sum over y, right? So to find x, I have to, 1 is 1 over 4, 1.5 is this, 2.5 is this, which is 1 over 4. So this is 1 over 4. So this is 1. What does this mean? It means that if we know that x is 2.5, then we know that y is, for sure it will be 4, because there is no other way, there is no other possible values for y to be. So this distribution, f of y given 2.5, and y, I have only one value, 4, and its probability is 1. However, what if I ask you, find f of y given that x equals 1.5? If x equals 1.5, we know that y can be either 2 or 3, right? Either 2 or 3. So I need to find the probability for each situation. So what's f of y equals 2 given that x equals 1.5? I need to find f of y given equals 3 given that x equals 1.5. So I have two options. So the first one, this is f of y equals 2 and x equals 1.5 divided by f of x equals 1.5. And for the other one, it's f of y equals 3 and x equals 1.5 divided by f of x equals 1.5. So for the first one, this is equals, what's f of y equals 2 and x equals 1.5? Y equals 2 and x equals 1.5. So this is 1 over 8 divided by x equals 1 over 5. What's x equals 1 over 5? It's this. It's 1 over 4 plus 1 over 8, which is 5 over 8. And let's see the other one. F of y equals 3 and x equals 1.5. Y equals 3 and x equals 1.5. It's 1 over 4. And divided by f of x equals 1.5, which is the same as 5 over 8. So this is 1 over 5. This is 2 over, I have something wrong. What's f of x equals 1.5? It's 1/4 plus 1/8. 1/4 plus 1/8 is 3 over 8, not 5 over 8. So so this is 3 over 8. Which means that this is why I suspected that there is a problem, because they should add to 1. So this is a new probability distribution. This is f of y given x equals 1.5, and this is y. We know that y can be either 2 or 3. So when it's 2, it's 1 over 3. When it's 3 is 2 over 3. Why? Because f of x given y is a probability distribution. It's a probability distribution, which means it should be positive and should add to 1. So conditional probability is a probability, which means that it should add to 1, and it should be always positive. طيب. The last thing I want to talk about today is the notion of independence. And independence is the same, more or less the same definition that we talked about before, but it becomes more important here because we are talking about joint probability distribution. And as we will see, in some random experiments, if the two, we'll study how the two random variables will behave if they are independent. How would they jointly behave if they are independent? طيب. So let me state the condition and then we do an example. So for discrete random variables x and y, we say x and y are independent if one of the following is true. Condition 1 is that the joint is just the product of the marginal, f of x times f of y. Like, if you recall, we had before, probability of the intersection is just the product of the probabilities, or f of y given x equals f of y, or f of x given y is f of x. So any of those conditions, if it is fulfilled, then it means that x and y are independent. So let's see this example. It says that in a plastic molding operation, each part is classified as it conforms to color and length specification or not. So we define, we have random variable x. X can be 1. We say x is 1 if part conforms, so it matches the color criteria, color spec, and 0 if part does not conform. And we define y as y is 1 if part conforms to length specs, and 0 if part does not conform. And we are given the joint distribution. The joint distribution is given like this. So this is x, this is y, and they are both 0 with probability 0.0002. X is 1 and y is 0 with probability 0.10198. Y is 1 and x is 0 with probability 0.0098. And the product conforms to both color and length with probability 0.97002. So now I can ask you, are x and y independent or not? Or let's find what's f of x. Let's find f of x and f of y, right? To find f of x, we need to sum vertically. So if you add those two, this is 0.99 and this is 0.01. So this is f of x. So f of x, f of x, we know that x can be 0 or 1. 0 with 0.01, 1 with 0.99. And then let's see y. So y I do it this way. So y is 0.98 and 0.02. So y and f of y can be 0 and 1 with probability 0.02 and 0.998. So are they independent? Are x and y independent? We need to check if f of x and y equals f of x times f of y, which means that we need to check is f of x times f of y will give you the joint, does, when we multiply 0.99 times 0.98, does it give us this? When we multiply 0.99 times 0.02, does it give us 0.198? And so on. So we need to check f of fx of 0 times fy of 0, which is 0.02, 0.01, sorry, 0.01 times 0.02, which is 0.0002, which is the same as f of 0 and 0. So we multiply them. This is f of 0 and 0. Let's check f of x 0 times f of y at 1. F of x at 0 is, sorry, 0.01. F of y at 1 is 0.98. And this will give us what? 0.0098. 0.0098, which is exactly f of 0 and 1, and so on. If you check the rest, you find that f of x and y is just f of x times f of y, which means x and y are independent. Final note. Given two discrete random variables, x and y, we the joint distribution should have a complete rectangular space of probabilities for us to be able to check independence. If the shape is not a full rectangle, it means that they are not independent. What does this mean? So if I give you something like this, like we did for above, this is x, this is y, and I told you I have some probabilities that looks like this. A complete square or a complete rectangle? No, we are missing. So if we do not have probabilities at the red dots, it means x and y are dependent. However, if we have dots, which means we have a rectangle, then you need to check. You have to check because in this case they can or cannot be independent. How do you check? You find f of x and f of y. So you sum to find x and to find y, and then you multiply each one of them to check if it gives you the constellation point. So basically, having a rectangular shape is a necessary condition but is not sufficient for independence. Okay, so with this I will stop at this point, and we'll continue the rest of the chapter on Wednesday, inshallah.